1, chapter 3b on vectors and relative motion. Okay, so I've already done the first part on projectile motion, whether it's launched horizontally, or the range problem when it launches and lands the same spot. So this is finishing up. This is actually the beginning of the chapter, but we'll be doing this, and I'll be showing you the graphical method using the PHET program for vectors. And I'll show you the simulation on that, and that's how you can do a lot of the problems, because it's a very nice system of doing things. So, to start with then, let's define the vectors then. So we have everything is in the x, y axis. We define it from the center point. And we have a vector, say, like so, and let's say it's 10 centimeters in length, and this is the angle. Let's say in this case, say 30 degrees, I'm just approximating it. We define a vector as the length, what we call the magnitude, and the direction is given by the angle. All right, so that's how we define a vector. Doesn't matter where it's actually centered. If I was actually to move this up to here, as you see from the picture, it makes no difference. It's still the same vector. It's just the length and the direction it's pointing to. Now for this, we have the x component, we have the y component, I should say the y, and we have the x component horizontal there. X is, and this is the r, let's say call this r resultant, is r cosine of the angle, and y is r sine of the angle. And then the r, using Pythagorean's theorem, r squared is x squared plus y squared. All right, so that's how you would define if you want to show the components of it as far as that's concerned. So that's what I define as a vector, and again, it's the length and the direction is pointing, not where it starts from. All right, so in this chapter, we're going to be using the graphical method of adding vectors. All right, so there's a component method where you can break each vector down to its component and add them that way and get the result. I'm not going to be doing that. That's in section 3.4, which is a rather lengthy section. I'm not going to be doing it. I'm going to be doing it by graphical method. So I'm going to use a graphical method. And we'll start with that. Okay? So that's the method we're going to use, and I'll demonstrate this with the PHET program in a little bit. Okay, so let's move on here. And so let's say I have two vectors. One has length 10 at the angle theta. One is 30 degrees, and the other is 6 centimeters with an angle of 45 degrees. All right, so I'm going to try, again, draw my scale roughly, but I'll use the same scale. So approximately 30 degrees. And I'm going to use this on a scale of, let's do, well, instead of 10, let's do 20 centimeters. And instead of 6, I'll do 12, because then it looks bigger on the picture, because I'm going to use actual centimeters. So about 30 degrees would be like so. and that would be the first vector. Now I'd add the second vector, which is 12 at an angle of 45 degrees relative to the horizontal. So the horizontal is like this, right? So it would be 12. And again, I'm just approximating the angle. That's a little too much still. And that would be B. So that would be 12. This is 20. This is 45 degrees. Again, it's relative to horizontal, not from the previous line. So the result of this, if this is A and this is B, then vectors A plus B, which is C, and we use a line over top of that, would be from the starting point of A to the finishing point of A, tail to head, tail to head. And we would draw that line. You can measure it. And that turns out to be about, all right, this turns out to be about 31 centimeters. So C would be 31 centimeters in length, and the angle would be approximately 40 degrees or so. All right, here's 30, it's not quite 40. So that would be how you would do the result of that, all right? Draw up the scale. You can draw up the scale, then measure. So this is called the graphical method because we're just doing it on graph paper. All right, so that's one example there. All right, now, again, it's tail to head, tail to head. So let's do another one. And I'll just do these as kind of arbitrary. So say I have this one. Okay, A. This one is B. And the third one is C. And I want to add A plus B plus C, all right? So you can, again, do these in any order. It doesn't make any difference. A plus C plus B is the same thing. So this is some resultant. So the way you would do this is you have to have tail ahead. So again, the direction and length is all that matters. So I would take this one, bring it up to here. So that would be roughly, so I'll use black for that. And I'm just going to approximate the length. Okay, that would be B. So A to B. And then C would be like so. Okay, this would be C, and the result would be from the start to the end of C. This would be our result. Right? You would measure the length of that, and then that would result. So you can move it so it's again tail to head, head to tail to head. All right. Now, a couple things while we're at this. If we have a vector A, like so, then minus A would be just in the opposite direction. Same direction, but same pointing, but in point in the opposite direction. All right? So that's how you can add any vectors. Or if I had a vector D that was like so, something pulling, so it could be forces. D, then D would be added to here, and that would be my result. So you can add any of them, this would be the result. So it's tail to head, tail to head, tail to head, and you can do them in any order you want. If I did it some other order, so if I did C plus A plus D plus B, I would still end up at the same point. So this also could be an example if we had, this would be in forces. So if we had forces pulling this way, pulling that way, pulling that way, pulling that way, then that result would be pulling it up that way. All right? So we can represent it any way we want, but this is the graphical method of doing vectors. Okay, and I'll go through that with something using the FET program. You can use a ruler to get length. You can use a protractor to get the angles precisely. But this is a good approximation for that. All right. So that's the section on vectors. All right. Last thing I'm going to do is on relative velocity, and I'll do a couple examples here, right? So relative velocity, and we're going to do this when we're going at an angle. All right. And again, I will do this somewhat precisely. So suppose we have somebody wants to cross a river that's 2 kilometers across. All right. And the current in the river is 5 kilometers per hour, about 3 miles an hour. Okay. And I have a boat. All right. That, you know, we'll do it in a couple of cases. We'll have a boat which has unlimited power. All right. And say it does 10 kilometers, you can do 10 kilometers per hour. Not a fast boat, this is a pretty small one. 10 kilometers per hour, about 6 miles per hour. All right. And I want to get across the fastest, so it goes straight across. All right. What is going to happen, and where am I going to end up when I do that? I mean, if you think of it, you aim straight across, much like we have the Lufthansa plane. If you aim straight across and you have a crosswind or cross current, you're going to get drifted to the right. Well, the question is, how do we calculate that? Well, the way we can do it is do it as a vector. We have, this is 10, this is 5, and I'm going to do this to scale. And I'm going to do a scale of 2 centimeters equals 1 kilometer per hour. So 20 centimeters is going to represent 10 kilometers, 10 centimeters will represent that. So let's start from here. Go up 20 centimeters, represent 10 kilometers per hour. So that's 10. And then I'm going to go, and the boat is, this is going to take me over 10 centimeters. And that represents 5 kilometers per hour. All right, what's the result going to be? Well, the result, if I have the right scale, this is where I end up. I'll end up actually crossing at this is 22, so I'll actually cross, this will be 11 kilometers per hour, right? 11 kilometers per hour. I'll be downstream, but this will be the fastest way to cross. Now, if this is my speed, and this is my distance, x, then the time it takes, remember velocity is distance over time, so time will be distance over velocity, which would be 2 over 10, 2 kilometers over 10 kilometers per hour, and that would be 0.2 hours. So it'll take me 0.2 hours across, but I would be quite a ways downstream. If this is 2 kilometers, then this is half of that. I would actually end up, this would be 1 kilometer downstream. So I'd end up 1 kilometer. So this is 2 kilometers it takes to go across, but at the same time, you're being blown by that. So you would be downstream by 1 kilometer, all right? So that's one way of doing it, is you want to just get across and don't worry about recross. The second option, and I'll leave this up here, so it takes 0.2 hours. So aiming straight across, the time is 0.2 hours. All right, now instead of that, say I want to go, instead of being blown downstream, I actually want to go straight across. Well, we're going to have to do in that case, the boat has a limit of 10 kilometers per hour, all right? So again, this was 10, this is 5, I end up crossing at a speed of 11 kilometers per hour. The second case, I want to go just straight across. So in that case, I'm going across, right? The water is blowing me this way, 5 kilometers per hour, but I can only go 10 kilometers per hour across. All right? This is the limit I can do. I can do that, but I'll be blown across that way. All right, so what do I do then? How fast am I actually going to cross then? All right, I'm going to again do this to scale. So I'll do, again, okay, this is straight down. I use this just to, all right, so what I need to do is represent this by 20. Okay. So from aim at, this will be 5. Collar's pushing that way. I'm aiming this way at 10. So this will be my result. And what will that be? What I'll end up doing is crossing at, let's see, this will be 18 centimeters, which is approximately 9 kilometers per hour. Now you can also see, so it's approximately 9 kilometers to cross if I do the graphical method. And the time then, if I'm trying to cross, so the time will be distance over velocity, which would be 2 over 9 kilometers per hour, which would be approximately, let's see, 0.22 hours. I can get this more precisely if you realize this is a 10, 5, this is half of that. This is actually 30 degrees. And so that's half, this is actually, in that case, cosine of 30 is 0.866. So precisely, this would be 8.66 kilometers per hour. But 9 is close enough, all right? And the sine of 30 is 0.5, right? So in that case, we go across, we aim for here, so we end up at exactly that point. So we're gonna aim at an angle of 30 degrees and we'll end up right where we want to be. Okay, and then we'll cross there. So that's the second case of relative velocity, and that's basically all chapter 3 is concerned. So now I have to show you the examples with the fat. Okay, for this part of the lab, this is chapter 3 link, and I'll have a link for the videos. So here's last year, so here's already 3A, projectile motion. Here's a link for the physics simulations, and here's one for vector that we're going, and then so I click on this one because we're going to use this simulation to show how we can use vectors using components, as I just explained for the section. Okay, so we're going to do a graphical thing. So you click on the lab, because this is all we're going to be doing with this part, and this has a simulation. So it's vectors, x direction, y direction, and you can click on these things here, values, angle, and the grid. So if you want to get rid of the grid, but we're going to keep the grid, and we will select a vector, and if we start it here, all right, and put in the value. Now here we have up here, but we can display a value with it, and the angle above the horizon. So as we change this, all right, so this particular one has length of 14.1, 45 degrees. If we go straight up, then it's 90 degrees, like 10, whatever we want, 0. So it's always the angle relative to the horizontal. So that's it there. And if we want to add the components to it, the x component and the y component. So for this particular one, again, to explain, the x component is the hypotenuse times the cosine of the angle, which in this case is 33.7 degrees, and the y component is 18 times the sine of 33.7. But to keep this a little simpler, we're not going to have the x and y components. We're not going to do it in terms of component method, but you can use this by doing the graphical method. So we'll now add a second one. All right. Oh, if we add a second one, all right, they need to be the same. So you gotta make sure they're the same value. So then if we add a second one, right, the second one has length 10, again, bring up the components, 6 and 8. Again, we're going to get rid of that just for simplicity. So if we were to add two vectors simply, right, so say this A and this B, and add them, again, if we go past 90, something like this would be like 116 degrees. All right, so it gets an angle from the positive x-axis. If we include the sum then of this, that's tail to head, this is the result. And we can do that by putting one at the result. So we start there and we end up here. So this would be the resultant of adding these two vectors. And as I rotate this, if I move this other one, right, we can see what the result is. So it's a very nice way of doing it. If I add a third one, right, and then tail to head, tail to head, tail to head, tail to head, all right? And make this arbitrarily. Then that's the result there. So this 18 plus this 18 plus this 10 with these particular angles, result is the result is 38.6 and an angle above the horizon of 31 degrees. All right, so that's one way of doing it. Now, let's clear this, all right? And I'm going to put this a little bit more centered, all right? Because what we have is some problems where we can do this in terms of distance. We can relate this to anything we want. So sometimes we'll be dealing with forces, all right? When you're moving in motion, you know, you go from one distance to another place. What's the result of where you started from? All right, that's what we just did. But sometimes you have opposing things that happen, like a force. So say we have an object. Oh. Now, before we do that, I should say a vector is only defined by the direction it's pointing and the length of it. Right? It's only the direction. So these two vectors are actually identical. And we're going to see what that means in the next place. So, so again, when we do motion, this is where we're going to end up with. We start here, we go up to this point, we go to that point. So how far away from where we started, this is the result here. Right? So if we clear this one, start over, put this here. So what we have in chapter 4 in particular, when we talk about vectors, sometimes you have things pulling on each other, like you pull one way, pull the other way, what's the result? So an example would be, instead of having this as being distance, we represent this as a force. Right? So this would represent, say, 10 pounds or 10 newtons. The result of this would be a force of 10 newtons to the x. Now, suppose we have another force in the opposite direction. Right? Intuitively, let's get that 10. Intuitively, it'd say this one is pointing that way, this one's pointing that way, so they're opposing each other. So the result should be 0. Well, how can we see that? Well, we can see that by moving this so that's tail to head, and the result is this one pulls that way, that pulls that way, so the result is 0. Which can make sense. So that's the case there. If we have one that is, say this one is 15 and that's 5, the result is going to be 5. Right? Go 15 back 10 is 5. Right? So when they're opposing, that's the case there. Now let's clear this and start over. So let's say you have a slightly more complicated problem. So say we have one force is pulling this way, right? Another force is pulling like that. And a third one is pulling like that. Okay. What would be a result of that? If we label this, let's get rid of the angles. We could put them in, but to make it a little easier to look at, I'm going to get rid of the angles. All right, what would be the result of all this? Well, I mean, I could put in the sum, but what I could do, all right, here's what the result is, all right, down here, all right. So what I could do, see, that's the result. What does that mean? How do I get that? How can I do that and know I have it right? Well, all I can do is take this one, take the second, move any one you want, move tail to head, and we see that this is the result is that one. We could even do it differently. We could do this one as so, and move this one, again, tail to head, and the result is the same. So this is when we started with this. This is how we can do it by using the graphical method. All right, if I was to do it as a component method, I would find each of the components, add all the x components up, then add all the y components. So this is plus 10, this is minus 11, and that's 0. And then using Pythagorean's theorem, figure out what the result would be. All right, so you can do it that way, but it's much more complicated than trying to do it this way. And if we add more vectors, it makes no difference. It's just we do tail to head, and there's the result for that. All right? So it doesn't matter how you order them. You just do tail to head, and that's the result there. So this is how you can do a lot of the lab problems. This is also how you could probably do the problems for the exam when they come up. So that's the component that's the graphical method using the fetch program on there. So I'll put it, you can click the link on there and go from there. Okay, so, all right. Okay.